All right, lesson 1-7. As we get started today, 1-7, we're going to have a bit of a transition. So we've been working on polynomial functions, doing all kinds of things with them. Now we're going to start what's called rational functions. And so on rational functions, what we'll be able to do is to describe and explain the end behavior. That means the limits as x goes without bound, either to the left or the right, to negative infinity or positive infinity. And we'll be able to graph and describe its key features. So we might begin with the question, what is a rational function? So if you go to your slide right after this vocabulary here, you go right after, this will tell us that a rational function, on this slide, a rational function is any type of function that can be written in this form. Said another way, it's like a polynomial divided by another polynomial. Thank you. Now, it's a polynomial divided by any other polynomial. That's what a rational function is. This is a rational function here. Now, question, in mathematics, there's one value, rational function. Sorry. My question for you, in mathematics, you're never allowed to divide by what number? 0. So this is going to be a very important construct here that we understand. The denominator cannot equal 0. If you read your note here, it says it'll look different. I call the curve that the graph will look like a C curve. So you might just mark this here, that these frequently look like C curves. A rational function will routinely look like C curves. Additionally, a rational function almost always will not be all reals. Because we will be dividing, there's usually a spot where mathematically it appears we're dividing by 0. So frequently we're going to have breaks. Not always, but most of the time we will have a break in the domain. So the domain will usually not be all reals with rationals. So what might our breaks look like? So speaking of breaks, let's take a look here. Oh, sorry. This is like a cheat sheet. I put this on here for you. If you're doing homework later on, that's your cheat sheet on what I'm about to work through this lesson. So I'm not going to simplify. I'm not going to describe this page. We're just going to practice it as we go. But that's there. So now, talking about the breaks. The rational functions can produce the two of the three types of breaks you'll see in mathematics. So on this slide, I want you to mark here that this one and this one, these graphs, these breaks in the graph come from rational functions. From rational functions. And they appear whenever our denominator would equal 0. If the denominator would equal 0, you're not allowed to do that. And the graph will break and look like either this infinite discontinuity or this removable discontinuity. So an infinite discontinuity is when, as you approach some x value, as you get closer and closer to that x value, the y values take off and either go to positive infinity or negative infinity. They do not have to alternate like this one. This has a graph that's going, as it approaches this x value c, this graph rises on the right, and on the left it falls. That doesn't have to be the case. They could both rise, they could both fall. But either way, if the graph at the break is going to an infinity, either positive or negative, then we call that an infinite discontinuity. Conversely, if our break just looks like an open circle, and just like an open circle, we call that a removable discontinuity. And I'll show you why in the equation form why we call it a removable. It has to do with you can remove something from the problem. But this is also known as a hole. So do this. We're going to add to your notes, put that this is a hole. And this over here, I didn't write it in. That's called a vertical asymptote. So on this one, put vertical asymptote. If you want to use your ID badge to kind of draw vertical, the asymptotes are usually drawn with dashed lines like that because it's not actually a part of the graph. That's why you use dashed, because dashed means it's not actually real. It's not a part of it. But it does just demonstrate where something occurs. Now in the middle, I'm skipping a discontinuity. This, if you're wondering, where does that come from? That's from a piecewise defined function. This is from piecewise defined functions. I've given you a number of those on Delta Math already, but that's where those come from. Okay, so now to talk a little bit more in depth about the asymptotes. We will have vertical asymptotes. We'll also have horizontal asymptotes. The next slide is just going to tell you about the vertical asymptotes. This one explains if you have a vertical asymptote, as the graph approaches some value, as the x values approach some value, the y's will either approach a positive or negative infinity.
We need all ninth graders to report to
A vertical asymptote will approach some line. The graph, whether it's going up or down, it can do either, but the graph will approach some vertical line, and we'll call that line x equals a on all of these. It's approaching some value, and that's how they would write it. Now, actually, this is not how we would write it in pre-calc. They wrote this in kind of how they teach you this in Algebra 2, but this we would actually write as a limit. So in this case, I'm going to translate this to proper limits. You would have limit f of x equals x arrow, and then the x is approaching a from the right side. That's what the plus means. So you'd have down here a plus, and this graph happens to be rising, so it'd be a positive infinity. That's how it would look as a limit. It's an ugly f, but that's how it would look as a limit right there. So that's how you translate that. That's all it's saying as a limit. This one would be from the left side, just rising. This is from the right side falling, and this is from the left side falling. You could write limits all the way across. I'm not going to do that here, though. Okay? Now, that's vertical because the asymptote's up and down. Next slide, there can also be horizontal. Now, horizontal is if you are going to the far left or far right, if the graph begins to flatten out and approach a constant. In this case, the constant would be b. And so the way a limit would work here is this graph, it's the right side. The x's are approaching positive infinity. And you would say it's approaching this constant line of, or constant value b. Whatever b is, that's what it's approaching. And so that's how the limit would look there on a horizontal asymptote. Now we'll practice this a lot today as we go on, but that's just kind of for generalization on your notes. Okay, so with that, let's start some problems. I'm first going to take a look here at the parent function. So the parent function is just f of x equals 1 over x. So it says first sketch a graph of 1 over x. Now here's actually how I'm going to do it in the future. I'm going to go from algebra. The first question I'm going to ask you is when we do a rational, what are you not allowed to divide by? 0. So the first thing I'm going to find out where the domain does not exist. The domain will be all reals except for where the denominator equals 0. So you're not allowed to divide by 0. There's nothing to solve here, so that means my domain is going to be all reals except for 0. So just to write that out here so you can see it, it's going to be all reals except for 0. So it can be any other number, just not 0. If you wanted to, you could write it out long ways like this. Negative infinity to 0, union, 0 to positive infinity. This is saying the graph will exist everything to the left of 0, and this will be everything to the right of 0. But since it's a parentheses, it will not include 0. So you can say it either way. Now, in the future, I will do that first. And the next thing, before I ever do range, increasing, decreasing, any of those, is I'll come down and I'll talk about then holes and vertical asymptotes. This will describe the break. So we have a break at 0. That's what we're saying in the domain. Here's the rule. If that x in the denominator can be canceled out, that factor can be canceled out in the numerator, it becomes a hole because you can remove it. If it cannot be canceled, it's a vertical asymptote. Does this x cancel with anything in the numerator? Can it be simplified? Can it be removed? No, there's nothing to cancel. So we will not have a hole, because nothing canceled, but we will have a vertical asymptote at x equals 0. So what I'm going to do is come to the y-axis, draw a vertical line, and make it dashed. Let me put on here x-axis, y-axis. Make it dashed like that. Now, so far, all that I've done, that's on that cheat sheet that I skipped over real fast. Later, if you're doing your homework, you can use that cheat sheet to help you out. Okay, from here, I'm going to move on, and I'm going to do horizontal asymptotes. And this time, it's actually going to be singular, so I'm going to take that away, that S, and this is also vertical asymptote. There's only one of them, so I'll take away the plural. Horizontal asymptote. It follows 3 rules. You look for the degree, and you check to see if the degree is bigger in the top or bigger in the bottom. Remember, degree means highest power. Now, this does not have an x, so it's kind of like x to the 0 power. This is x to the first power. Which one has a higher power, the numerator or denominator? Okay, we'll call this rule Bobo. Now, what does Bobo mean? It means your power is bigger on bottom. Bigger on bottom. That's what the Bob stands for. Bigger on bottom means your horizontal asymptote is going to be y equals 0. That's where the last O comes from. Bigger on bottom, it's y equals 0. So I'm going to add that asymptote now. To my graph, I'm going to have this asymptote. Again, everything I'm doing, it's on that cheat sheet, but I'm just showing you how I'm going to do it today. So after I do holes, vertical asymptotes, after I do a horizontal asymptote, I'll then do the y-intercept. The y-intercept you get by plugging 0 in for x, substituting x value of 0 in. So it'll be whatever we get when we do this. So I plug in a 0, and I get 1 divided by 0. Am I allowed to do that? What's the problem with that? Dividing by 0. Not allowed to do that. I'm going to draw a line through it. AP test graders do not like to see anything's equal to something divided by 0. So I'm going to erase that so they know it's not equal. F0 is undefined. And I'm going to make sure I write this properly. So it does not exist. You could have said NA from the get-go. But once I start writing out that math, and I have that equal sign, I need to get rid of that and say F0 is undefined. That means it will not cross the y-axis. Finally, again, all this is on the cheat sheet. If you need to find your zeros, you set the numerator equal to 0. And you solve. Right now I have 1 equals 0. Can 1 ever equal 0? No, there's no variable, so that there's not going to be any zeros either. NA, none. So from here on out, we will use the calculator, but this first graph I'm going to give you, it's this C curve that goes through the first quadrant like this, and it's going to approach either asymptote on either side of the first quadrant. So draw a C curve like this, and because my power is odd, this is an odd function, all the powers are odd, since that's an odd power. Since it's odd, it'll reflect across the origin. You remember that. If you have a odd power, only odd powers, it'll reflect across the origin. Or you can say it's symmetric with the origin. Symmetric with respect to the origin. You could write it that way. Or you can just say it's an odd function, which is a lot easier to say it's odd. Okay, the last few things I haven't filled in yet. Let's take a look at the range here. Range means y values. How low does this graph go? Negative infinity. How high does it go? Positive infinity. Is there any break in between this? Any separation between the two pieces? 0. So it is very similar here. This one will be y does not equal 0, and that's because it's odd. If it were even, it would be different. And again, y is all other reals. Whoops, I put an x. Y is all other reals. It's just not 0. So you could write it that way, or you could write it this way. Negative infinity to 0, union 0 to infinity. All numbers except for 0. That's what we're saying. And finally, looking at the graph, does it increase or decrease? Let's take the first piece. What would happen here? Increase, decrease?
Decrease.
Decrease. What about here?
Decrease. No,
It also decreases. It never increases. Never increases. But if it's always decreasing, we could say, if you wanted to, it strictly decreases on its domain. So you could copy down that domain again. I'm just going to say it's strictly decreasing on its domain. So that's the gist of the parent function. So for the rest of the day, what I'm really going to focus on are not these review items. I'm going to do the new ones. So I'm going to do domain, followed by holes, vertical asymptotes, horizontal, y-intercept zeros, and then limits. Those are the things we're going to look at, and we're just going to give a lot of practice. Again, if you're at home and doing this, you have this cheat sheet right here to help you find those values that I'm going to be describing as we go on today. There was that word bobo I used a moment ago. Okay, with that, let's look at our next example. All right, now we're going to look at example 2. Now what I'm going to do a little differently is I'll just paste my graph, but as you go, as we graph them, I would just do a quick sketch for yourself. So here's the order I typically go in. I'm going to first say, what is our domain? And we get the domain by saying, what's the only thing you cannot do with this in mathematics? Divide by 0. So to get this value, I'm going to say the denominator cannot equal 0. Now how would you solve that? Plus 1. And so what can x not equal? X cannot equal positive 1. So there's my domain. X cannot equal positive 1. What can x equal?
Anything else?
Anything else. So just to make sure that's clear, I'm going to do XER. That means all reals except for 1. Again, if you want to write it out long ways, you can. It would be negative infinity to 1, parentheses, union, 1 to infinity. That means all reals except for the 1. That's what the parentheses means. It does not actually contain 1. I'm going to skip these right here, the review items. And I'm going to go to holes. So what's a hole? Let me go back to the problem. A hole is if you could cancel a factor in the numerator and denominator. So on this one, I can't cancel it. Students may think, well, can't I cancel those x's?
No.
I'll prove to you we can't. Let's just come up with let's just pretend we have a number for x. What's a good number y'all like?
12.
Here, 12. What if we use 12 for x? If I said this is 12 minus 1 like that. Now, without canceling, what would we say this could be simplified to become? 12 minus 11. Well, if I did think I could cancel, we cancel that, and maybe you say, well, since it's 12 divided by 12, that should be a 1. What's 1 divided by negative 1? Is it 12 over 11? No, that didn't work. Well, what if you say, well, it cancels. Shouldn't it be a 0? Well, what's 0 divided by negative 1? Is it 12 divided by 11?
No.
See how the math doesn't work? You can't cancel terms, is what that's called. You can only cancel if it's a full factor. So since nothing cancels, it's not a hole. A hole comes from a removable discontinuity. We'll remove it if they cancel. So there's not a hole. So if it's not a hole, what is that discontinuity? It's got to be a vertical asymptote. So we have a vertical asymptote at 1. Now a vertical asymptote is not actually a part of the graph. That's why I'm going to say x equals 1. The domain tells you where the graph is. This tells you what's filling the space where it's not. So on our graph, if you go to the x-axis at 1, and I told you earlier I'm going to paste a graph in, this graph would be in here. Maybe I'll start doing it on the next one. Since I'm already this far, I'll draw one more by hand. That would be our vertical asymptote. X equals 1. Now that's not actually part of the graph. That's why we're saying it's equal to it. The actual graph will not equal that spot. Now the next thing I do is I go to horizontal asymptotes. Now this is figured off of the degree. What's the degree of the numerator?
1.
1. What's the degree of the denominator? 1. And so you ask yourself, are these exponents, the degrees, bigger in the numerator, bigger on top? Are they bigger on bottom, or are the exponents the same?
Same.
The same. So the rule, if you look on the cheat sheet, says exponents are the same, DC, divide coefficients. Exponents are the same, divide your coefficients. So the equation will be y equals, how many x to the first do I have in the numerator? 1. And how many x to the first do I have in the denominator? It's just going to be 1 divided by 1. What is 1 divided by 1? 1. So we're going to go to positive 1 on the y-axis, and we're going to add a horizontal asymptote. Right there. That's y equals 1. Now the y-intercept is found by substituting 0 in for every x. So mathematically, the way you would write that is f of 0 would equal, and you substitute a 0 in. 0 divided by 0 minus 1. Which could simplify to be 0 divided by negative 1. And what is 0 divided by negative 1? 0. We have a y-intercept at 0. Let's put that point on there. There's our y-intercept. And finally, the last thing. The zeros of the function are determined where the numerator equals 0. So you'd set that and you would solve that. Well, it's already solved for us. What do we get there? X equals 0. So from here we could graph. I have to approach these asymptotes. I know it's going to go through this point at the origin, so this one has to go towards this asymptote. This one is going to come like this. Now, because the powers are odd, it's not actually an odd function. I'll describe that in a second. But because the powers are odd, this will it will reflect across our asymptotes, kind of like reflecting across the origin. It'll reflect this way, and that's because the powers are odd. Now this is neither even nor odd though, because it doesn't have perfect symmetry on the origin. Okay, one more time. Range. All reals, not all reals. And all reals except for 1. Good. So all reals except for 1. I'm just going to write the short version this time. All reals except for 1. Does the graph increase anywhere? No. Does it decrease? Always. It's always decreasing. So let's look more in depth at this function. Ruby, how you doing over there? Ruby. All right, let's look at part B here. It says, prove whether the function is continuous. Now, if you're wondering, how do I prove something's continuous? Maybe you've seen this on Delta Math. You're like, how do I do that? For something to be continuous, each one of these values, the 3 limits and the function itself, has to have the exact same answer all the way across. Okay, so I'm going to copy our picture that we just had right here. So if I copy this picture, let's take a look at what we get here. Whoa, that's huge. And after this, I'm going to just start using Inspire. Sorry, I got to shrink it up quite a bit. Okay, this one. As we approach the x value of 1 from the, what does that negative mean? Just before 1 or coming from the left. As we approach x equals 1 from the left side, so this piece, what's happening to the graph? Am I rising, falling, or getting flat? It's falling. And what symbol represents falling? Negative infinity. So let's say this right here is negative infinity. You know how I'm going to do this? I'm going to say that's negative infinity, and I'm going to call this limit 1, and I'll put a 1 down here so you can look back later and realize that limit corresponds there. Now limit 2. This says 1 plus. That means just to the right of 1, or you could think of it as approaching from the right. As the graph gets closer and closer to 1 from the right side, what do? Rise or fall? We rise. What symbol means rise? Infinity. So I'll put a 2 here. Now the third limit compares the first 2. Are these 2 values the same or are they different? They're different. The third limit says if they're the same, you get an answer. If it's not, then this does not exist. This limit does not exist. D, N, E. That limit does not exist. Because these are different. And then finally, f of 1. That means where is the graph actually at 1? Where is the blue graph at 1? Is it actually there? Not there at all. This would mean undefined. This would be undefined. Let me change my color. F1 is undefined. That's because it's not there at all. Now, so are these the same all the way across? Did we get the same value all the way across? No. If even just one of them is different, then it's not continuous. The function f is not continuous. Not continuous at x equals 1 for a variety of reasons. It's because this does not exist, because these aren't equal, because this doesn't equal those. So f is not continuous at x equals 1 for that reason. Now, one more thing before we move on in this example. Describe the end behavior. Let me copy this as it is this time so I don't have to shrink it one more time. We want to describe the end behavior. That means the limits as you go to the left and the right. So let's we'll do the one that goes to the right over here. Let's describe the end behavior as x increases without bound, meaning it goes to positive infinity. As this graph goes right, what happens to my y values? Do I rise? Do I fall? Or does it get really constant and flat? It actually doesn't keep falling. It approaches this asymptote. What's it doing as it gets closer to this asymptote? It's getting really flat. What's the y value it's getting flat with? 1. So it would be approaching 1. Now what's the end behavior over here? As we decrease without bound, as x decreases without bound, meaning as we go to the left, does my graph rise, fall, or get flat?
Fall.
As we go left, the graph gets really flat. What's the y value it's getting flat with? 1. Now that's where the horizontal asymptotes come into help. Here's a typo. I should have said describe the end behavior using its horizontal asymptote. That's all I needed to say, not the vertical. You would just use the horizontal asymptote. And there it is. Yeah. Okay, to save us time today, and so we're not kind of just losing our mind trying to graph some of these, what I'm going to do is we're going to graph it in Inspire, and then I'm going to walk through why the values are as they appear. Okay, so starting on this next example, example 3, we're going to graph this, and then I'm going to show you how we get those values. And I'm going to drop the review stuff. We're just going to look at the domain, holes, vertical asymptote, horizontal, intercept zeros, and limits. Okay, so let's first go graph this. Open up your Inspires. X squared minus 4 divided by x squared minus x minus 6. That's the function f that we're going to graph. Wrong one, Kevin. Inspire. So to get a fraction, you can hit Control Divide, and it'll give you that fraction line. It was x squared minus 4 over, what was it over?
X squared
Minus x minus 6. Okay, now this is going to be our graph. And so all I'm going to do here is take a picture of this, and then I'm going to bring it over, and we'll kind of work as we go and explain as we go. Don't start drawing this yet, because I want you to have some space to write out the math that occurs. But this will be our graph. I'll go ahead and put this down here. So we'll have it here for a little bit. All right, so as we get started, here's how I would do this problem just purely using algebra. The first thing I would do is find where my domain does not exist. What is it in math that you're not allowed to do?
Divide by 0.
Divide by 0. So I want to find where the denominator does not equal 0. This is a trinomial. What did we learn back in lesson 1-5 about factoring trinomials? What method do we use? X method. I'm going to try X method. If you remember X method, it's where you put a times c value up top, and the b value down below the x, where a is referring to the number of x squareds, b is the coefficient in front of x, c is the constant. I don't have a number of x squared, so what is my coefficient then? 1. And so 1 times negative 6 is negative 6, and my b value is negative 1. Remember, you're looking for a product of negative 6, a sum of 1. What are the factors of 6? There's 2 and 3, and there's 1 and 6. Which one could combine to give you a 1? 2 and 3. So it's going to be 2 and 3. Now let's think about the negatives. How do I make it be a negative 1? Negative 3. Perfect. So now, from here, what does this mean? And we're going to do this as we go. We will factor it as you split the a term's power, if you remember. So instead of it being x squared, you're going to have 2 different parentheses of x. And it'll have a plus 2 and a minus 3 inside each factor. Like that. X plus 2, x minus 3. Those are my factors for the denominator. So this is not allowed to equal 0. So my domain here, if this cannot equal 0, one more time, this cannot equal 0. What would x have to be here to get a 0, according to the zero product property? A minus 2. So x cannot equal negative 2. Now what about this factor? What can x not equal here? 3. X could not equal negative 2 or positive 3, but it could equal any other real value. Any other real value it could equal, just not those two. Now to find out if this has any holes, we need to factor the numerator. This is a difference of squares. You might remember that shortcut, but I'm going to act like you don't. I would do a times c up here with b. B's missing. So what's b if there is no x term? 0. It's like you have 0 x's. So let me actually make this c more in place here. Put c there. A would be here. So I'm going to do another x method in case you forgot. This is just in case you forgot the difference of squares. So 1 times c is negative 4. And b is 0. What are factors of 4? 2 and 2 and 1 and 4. Which one could combine to give you a 0? 2 and 2. To make it be 0, it has to be 2 minus 2, like that. So again, I split my a terms power, and so I have x plus 2 and x minus 2. So how does that help me on holes? I'll show you. A hole is known as a removable discontinuity. That is a, let me just make that note, that is a removable discontinuity. It occurs whenever a factor can be removed from the problem. You see how I just removed that? We will have a removable discontinuity at which x value? At negative 2. So that means on our graph, if you looked over here, we should have had a hole there. Did our Inspire show us a hole? So we're going to add an open circle right there. Let me get my tool so it shows up right. Fill it white with red. There we go. We should have a open circle right there at 2. Now, you're actually going to be responsible for knowing what the y value is. So if you're like, well, how do I find that? Let me tell you. We know the x value is at negative 2. If you're like, what is that y value? Is it 1? It looks like it's close to 1. How you know is you plug in negative 2 to the remaining equation. So just the unsimplified version, it'll be negative 2 minus 2 more divided by negative 2 minus 3. Let's simplify that to figure out what that point is. That would be equal to negative 2 comma. What's negative 2 minus 2 more? Negative 4 divided by what's negative 2 minus 3 more? What's negative 4 divided by negative 5? Can I turn it positive? Yeah, it's 4 over 5. And you could leave it as 4/5, or you could do it as 0.8. Very good. Or negative 2 comma 0.8. That's what that value is right there. That value, that point, is at negative 2 comma 0.8. That's where that would be, that open circle. Okay, so if the whole is this, the factor that cancels, the one that does not cancel, that stays there forever, is your infinite discontinuity, your vertical asymptote. This is known as a infinite discontinuity. Infinite discontinuity. It's the x value, the factor that does not get canceled, which is x equals what value? 3. Say 3. X equals 3. That's it. X equals 3. So I'm going to add that to my graph now. This is the infinite discontinuity at x equals 3. It should look like this right there. From the factor, the denominator that did not get canceled. That one right there. That's where it came from. That is x equals 3. Got it. Now, looking at the exponents, we're going to horizontal asymptotes. You look at your exponents. Are the exponents bigger in the top, bigger on bottom, or are they the same? Exponents are the same. If the exponents are the same, the cheat sheet says exponents are the same, divide your coefficients. Eats DC is what it looks like. Exponents are the same, divide coefficients. It'll be y equals, how many x squared do I have here? 1. And how many x squared do I have here? 1. It's 1 divided by 1. What is 1 divided by 1? 1. We're going to have a horizontal asymptote at y equals 1. There that is. Y equals 1. Say that again. Exponents are the same. Divide coefficients. By the way, those rules, if this on your very front of your packet, those acronyms are right here on this cheat sheet. So if you want to look back, exponents are the same, divide coefficients. Bobo is bigger on bottom, y equals 0. And if it's bigger on the top, we will not have a horizontal asymptote. It'll be oblique or slanted. Okay? We're not going to get into that for a while, though. All right, let me pick back up where we were. Where were we? Right here. Almost done. Y-intercept. How do you get a y-intercept? Say again. How do we get a y-intercept? Hey, Ruby, can you take out your headphone for me? You plug in 0. So, thank you, Evelyn. I'm going to ask that again. Class, how do we find the y-intercept?
Plug in 0.
Plug in 0. Moises, how do I find a y-intercept? Plug in 0. Good. Let's plug in 0. I would use the simplified equation here. It'll be easier. Or actually, maybe it won't be. If I use the standard, this one over here, if I plug in 0, what is 0 squared? 0. It just becomes 0 minus 4 over 0 minus 0 minus 6. Maybe it's easier this way. Which equals, all the zeros basically get simplified out of there. What's negative 4 divided by negative 6? 2 over 3, 2/3. That would be this point right there. That point would be 2/3. 0 2/3. That's 2/3 there. And the zeros. You get zeros from any factor in the numerator that's left over. If I solve this, what would I get here? If I said x minus 2 equals 0? 2. We have a 0 at x equals 2. That would be this point right there. that would be 2, 0. To finish off what's probably feeling like the longest problem ever. Let's fill in these limits. What happens as, this is telling us x goes what direction if it says negative infinity? Left. As this graph goes left, does it appear to be rising, falling, or getting pretty flat? Flat. What y value is it getting flat next to? 1. Remember, a limit doesn't tell you where the graph is, it tells you where it's going. It's heading towards 1. Now, what's happening as we go to the right? X approaching positive infinity. As this graph heads to the right, does it appear to be rising, falling, or getting really flat and constant? Flat and constant. Now notice I threw in extra limits here because I have 2 other discontinuities. Let's do this discontinuity at -2. So I'm going to have a -2 minus and a -2 plus. As we approach -2 from the left, usually I say, is it rising, falling, or getting really flat? Well, this one's different. It's coming to a point. What's the y value at that point? 0.8. 0.8, or you could put 4/5 if you prefer. Now, what happens as you come from the right? Is it rising, falling, flat, or I should say, coming to a point? It's coming to a point. What's the y value of that point? 0.8. Now, because these two are the same, because these two are equal, you could write it as one limit. You don't have to use the plus or minus. You could just say x approaching -2 of f of x would equal 0.8. You could just do it one time. You don't have to do the plus and the minus since they're the same. Since they're equal, the limit exists, and it's 0.8. Not to be misunderstood, f -2 would be undefined. F -2 is undefined because we have an open circle there. The graph does not exist at -2, so the function's not defined at -2, but the limits do exist. Okay, and now let's talk about it at 3. Let's go 3 from the left, 3 from the right. What happens as we approach 3 from the left? From the left, as we approach 3. Does the graph rise, fall, or get flat? Falls, but negative infinity. What happens as we come from the right? Rise, fall, flat. Rise. Are these equal to each other or not equal? Since they're not equal, that means the limit as x goes to 3 does not exist. You would say D and E. Does not exist. Does not exist. Since these two limits are not the same. All right, let's take a look now at example B. What would y'all like to do? Do you want to graph it first, or do the algebra and then see if it matches up with the graph later? Graph first? Okay, let's go over to the graph. Kevin, sit up here. It's like 4 times already. Let's go to our graph. 4x plus 20 is the numerator. Four x plus 20 is the numerator, and the denominator is x squared plus 10x plus 25?
Yes.
All right. So here's our graph that we're going to be working with this time. Okay, so as we start working through this, we'll compare it to the graph as we go. Let's have you start walking me through how to find these values. How will you get your domain here? Donna, do you remember, how do we find our domain? Yeah, we'll have to do the x method because what we're looking for is where the denominator is equal to 0. You're not allowed to divide by 0, so that's where the domain will break. So we need to do an X method to factor this. So again, here's my A, B, and C. So on my X method, what would y'all put in the numerator here? I should say numerator, the top of the X. 25. I agree totally. 25. And now the bottom is 10. Moises, can you think of any numbers that multiplies to be 25 but adds to be 10? 5 and 5. So it's not 1 and 25. It's 5 and 5? Totally agree. So when I factor this, this is called standard form. I'm now going to write it in factored form here. I will have an x plus 5 and another x plus 5. Do I need to write x plus 5 twice? What's a way we could shorten it?
X plus 5
Squared. Perfect. X plus 5 squared. We have 2 of those. So what does that mean x cannot equal in the domain? Positive 5, negative 5. Negative. You would set this equal to, say this cannot equal 0. You'd have to add the 5 added across, so it's negative 5. It cannot equal negative 5. What can it equal? Everything else. Okay, in the numerator. Oh, nope, sorry, going too fast. To find out, let's talk about negative 5. Is it going to be a whole or a vertical asymptote? Well, we can see from here what it'll be, but if you did not know, you would need to, at this point, factor the numerator. This is not a trinomial. It's a binomial. This will be easier to factor. Is there a GCF here? Yeah, 4. I'm going to factor by GCF. If I divide out the 4, what's 4x divided by 4? X. And now what's 20 divided by 4? 5. Ooh, this is tricky. Maybe I shouldn't have written this as a squared. I'm going to edit this. X plus 5. Now, what can I do here? I can cancel, which makes you think that's removable. However, there's still a plus 5 left over. So on a whole and vertical asymptote, the whole is kind of like more powerful. It's like it'll trump it. And since there's still a plus 5 remaining, I still cannot be negative 5, even after I cancel it. So we're going to have x cannot equal negative 5 as a vertical asymptote or an infinite discontinuity, not as a whole. Since, just so you're clear, there's no whole since x plus 5 still remains in the denominator. So even after we simplified, there's still an x plus 5, and that's why we don't have a whole. So let's go to our graph, and if you're adding like a quick sketch, you should have a vertical line at negative 5. 1, 2, 3, 4, 5. A vertical line at negative 5 to represent that vertical asymptote. Now that I do that, I go to horizontal asymptotes. Jesse, do you remember how to find the horizontal asymptote? Edwin, do you remember how to find a horizontal asymptote? Okay, well, I'll just jump in. It has to do with the powers. You compare powers. Are my powers bigger on the top, bigger on the bottom, or are the exponents the same? They're bigger on the bottom. That's an exponent of 1. This is exponent of 2. I'm bigger on bottom. The rule is BOBO. If it's bigger on bottom. Bigger on bottom, this O stands for y equals 0. So I'm going to add in a horizontal asymptote at 0. Which means my graph, though it cuts off, would be approaching that asymptote this way. Intercepts. Lorena, do you remember how to find an intercept? The y-intercept in particular? No? Okay, so I'll do some more practice until we get this down. you're going to plug in a 0. That's what you do. You plug in 0. So I want to use standard form just because I can see this will, plugging in 0 and all those first locations will cancel out. Or just paused on me. Let me try this. Let's try using a mouse here. So what will happen is this 4 times 0 cancels out, and so it'll just be 20 over. That's 0, 0, 25. It'll be 20 divided by 25. Could we reduce that? Yeah, what does that reduce to become? 4 over 5. That's correct. 4 divided by 5. And we've already had that once today. What is that as a decimal? Yeah, 0.8. Oh, my board's back. All right, 0.8. So I'm going to come over here and add that point in. That point right there is 0, 0.8. And now the 0. You solve the numerator equal to 0. I'm down to just 4 there. If I were to rewrite this one more time, I'm down to the equation 4 over x plus 5. Can 4 ever equal 0? No. So you don't have any zeros. And so that would be the appropriate graph there. Well, darn. Okay. And so finally, goodness, there we go. Let's do some limits. What happens as we go to the left? Does this graph rise without bound? Does it fall without bound? Or does it appear to get flat? Flat. It's approaching a horizontal asymptote. What's that asymptote? 0. Gets flat with 0. What about as we go to the right? Does it fall without bound, rise without bound, or does it appear to get flat? Flat. And so it's approaching the horizontal asymptote. 0 as well. Okay, what about, we have a break here at -5. Let's look at the left side and right side of -5. On the left side, what happens on the left side of this graph? It falls. -infinity. What happens on the right side? It rises. Are those the same? They're not the same? Since they're not the same, the limit at -5 would not exist. There's no other break, so I don't have to use this limit. I'm going to do it right here. This -5 does not exist because, I'm going to just erase that out of there, or how about I just cover it up? These would not exist because these two are not equal. So the limit at -5 would not exist. All right, I'm going to roll one more time through, and then I'm going to let you see what we can do on the practice problems at the end. So I'm going to do one more with you, and then we're going to see what you can do at the end here. Okay, what would you do first here? Define domain. Well, let's find what x cannot be. Do I need to do x method for this binomial? Or can I do GCF? Do we have any GCFs? 2x. And, okay, so what's 2x squared divided by 2x? X. 2x squared divided by 2x is x plus. Now 4x divided by 2x. 2. Good job, Jay and Jacoby. Heard you both. Good job there. Okay, there's that. So what can x not equal? You said we cannot equal 0. What about this here? We haven't done this yet. You have 2x cannot equal 0.
0.
I'm doing 0 product property here. Is that 2 or 0? 0. So we cannot equal 0. That's one value we cannot equal. What about inside?
-2.
-2. So there's two values we cannot equal. What can we equal?
Everything else.
Anything else. Now let's find out if they're holes, vertical asymptotes, or some combination. This I need to x method. So I have an A, B, and a C. What's A times C? -4, and my B? Okay, the factors of 4 were 1 and 4 and 2 and 2. Which one can somehow combine for a 3? 1 and 4. Now let's figure out the negatives. So remember the options are you can have a negative positive, a positive negative, positive positive, or negative negative. Which way gives us a -3? -4. 1 minus 4 is -3. Good. We split the A terms power, so it should become x minus, plus 1 and x minus 4. Can I cancel anything? If you can't cancel, what does that mean? Holes or vertical asymptotes? They're going to be vertical asymptotes, so we have no holes. The vertical asymptotes, we will have 2. We will have them at 0 and at -2. Both these values, I'll do it in order this time, -2, comma, 0, from left to right. Sorry I didn't graph first. We're just going to do algebra first this time, then we'll compare the graph after. Horizontal asymptote. Look at your exponents. Bigger on top, bigger on bottom, or are the exponents the same? Exponents are the same, so you would go off you would divide your coefficients. If the exponents are the same, you divide the coefficients. So it would be y equals 1 divided by 2. So you can leave it like that, or you can say it's 0.5, whichever you prefer. 1/2 or 0.5. The y-intercepts. How do we find a y-intercept again? Okay, so when we plug in a 0, I'm going to use -4, and the denominator I plug in 0, what am I left with? Alright, example D. This function. Alright, if I were going to begin with domain, I would first look at what can I, not equal in the denominator here. What can I not, I can't divide by 0, so I need to factor this. Let's take that away. And so to factor, I'm going to use X method for this trinomial. And so factors of 10 that add up to 7 is what I'm looking for, which would be 5 and 2. 5 times 2 adds to be 7. 5 times 2 multiplied to be 10. 5 plus 2 adds to be 7. It's 5 and 2. So I'm going to split my A terms power. So it's going to become x plus 5 times x plus 2, which I can now figure out in the domain. I could not divide by, you're not allowed to divide by 0, so if x is -5, I have a problem. If x is -2, I have a problem. But x could be all other real values. Now to figure out if they're holes or vertical asymptotes, I would now need to factor the numerator. So again, I have another trinomial, so I'm going to do X method. I'm now looking for factors of -20, that add up to be 1. So with 20, there's 1 and 20, 2 and 10, there's 4 and 5. I'm going to use 4 and 5. And to make it be a 1, it has to be -4. So 5 minus 4, or you think of -4 plus 5. So I'll write that out. X minus 4, split my x term power, and x plus 5. Now, looking in factored form, I can realize I can remove the x plus 5 factor. So that means I have a hole when x equals -5. I have a hole. So to find the exact coordinate, what I do is I plug in a -5 into the remaining portion of the problem. So it would be a -5 minus 4 over a -5 plus 2. I just plug that value in, -5, into the simplified form, which would just be x minus 4 over x plus 2. That's all I did there is I plugged in that -5. Now I'll simplify that and find out that my hole will exist at -9 divided by negative 3. Negative 9 divided by negative 3 is positive 3. Negative 9 divided by negative 3 is positive 3. So I'll have a hole at that location there. Now the other discontinuity, the negative 2, will be a vertical asymptote. For my horizontal asymptote, what I would do is I would check out my powers. My exponents are the same here. So I'll put each DC. Exponents are the same. The DC stands for divide your coefficients. So in this case, it's 1 divided by 1, which is 1. To find my y-intercept, I will plug in 0. You could use this reduced form. You could use the standard form. Either way, it'll become negative 4 divided by 2, which is the same thing as negative 2. Finally, for zeros, you find out where the numerator would equal 0, which in this case it'll be positive 4. So at x equals 4. So now we'll go over and look at the graph. We'll look at the graph and see what we get here. Alright, so f of x, x squared plus, I've forgotten already, plus x minus 20, and then we had x squared plus 7x plus 10. X plus 7x plus 10. Alright, here's our function we're seeing. I want to take a picture of this. Okay, let's check out our values. We thought it was going to have a hole at negative 5, so we should not see a discontinuity. It should just, what we'll do here is I'll fill this in, and since I'm in red, let me go red here. At negative 5, 1, 2, 3, 4, 5. Notice it doesn't look like it's broken there, but it actually is. So I'm going to just draw a circle like that and place that there. And the location we got for our hole is when we solved that, we got negative 5, comma, 3. And so if we look here, just to totally try to make this abundantly clear, this value right here should have an x value of negative 5, and the y value would be at 3. That would be the point of that removable discontinuity there. Let me move this up to the front, so order, bring to front. There we go. So you can see that's where the location of that point is, right there. The vertical asymptote should be at negative 2. So that would be here, negative 2. That's x equals negative 2. Let me add that to the notes. X equals negative 2. And of course, we'll have the y-intercept at 1. The y-intercept at 1, which is going to tell us our end behavior. It's going to help us out on that. Whoops, wrong color. Try that one more time here. Y-intercept at 1. Excuse me, horizontal asymptote at 1. We had a y-intercept at negative 2. Perfect, right there. 0, negative 2. And we also had a 0 at 4, right there. 4, comma, 0. And so if we fill out our information, what happens to the graph as we approach to the left? As the graph goes left, it appears to flatten out to this horizontal asymptote at 1. As we go to the right, again, it's approaching this horizontal asymptote at 1. What happens on our breaks? Let's see, at negative 5 to the left. On the left side, we are approaching, from the left side of negative 5, we're approaching this y value of 3. That's a 3 there. So that's approaching 3. And as we approach negative 5 from the right side, we are also approaching this point. It's not falling forever. It's not rising without bound. It's not getting really flat. It's coming to a point, and that point is at 3. So notice these two limits are equal to each other. Because they are equal to each other, the limit at 3 would exist. Not 3, I'm sorry. This is a negative 5 with a plus. The limit at negative 5 exists, and that limit is 3. You don't need the plus and the minus if it's the same for both, which they are. So you could just say it's the limit of at 3. Okay, those are all equal to one another. And now finally, if I did it at negative 2. So we'll do a negative 2 minus and a negative 2 plus. So what happens as I approach negative 2 from the left side as the graph is rising? It's rising to positive infinity. And as I approach negative 2 from the right side, the graph is falling. Notice these are not equal to each other, so the limit at negative 2 would not exist. The limit at negative 2 as x approaches negative 2 does not exist because they're different than one another. Alright. The continuity here, even though these limits are all equal to one another, it still would not be continuous, just to make sure that's clear, because at negative 5 that's not an actual point that's filled in, so f negative 5 would not exist. If I want to, maybe I'll add that over here. F of negative 5 is undefined. I said it does not exist, I meant to say it's undefined because it's a hole. Okay, that hole is, that's why it's undefined there. At negative 5, 3 is not a portion of the function. Okay? Now we've seen a lot. I'm going to show you just one more, and then it'll be time for your practice. Or no, we'll have a real world problem. So, look at this one. It looks like a ton of stuff's going on. But I see that there's a GCF. So, when I look across the denominator, I see they all could be divided by 3x. So that's the first thing I'm going to do is divide by 3x. And when I do, I'm going to have left over x squared. So my GCF is 3x. Now I'm going to get x squared plus 3x squared divided by 3x is x. And then negative 36x divided by 3x would be negative 12. So there's the denominator, and now up here I have a GCF. It looks like 4 goes all the way across. I could divide out 4 and I'd be left with 4x. I'm left with x squared minus 28 divided by 4 is 7. And then 48 divided by 4 is 12. Okay, to find my domain, I need to set the denominator equal to 0. I'm going to have to carry this on over here when I refactor this. So I'm going to give myself space, and I'm going to do x method for the denominator here. A, B, C. So I'm going to have factors of 1 times negative 12, that's negative 12, that add up to be 1. So the factors of 12 are 1 and 12, 2 and 6, 3 and 4. To get a 1, I've got to use a 3 and a 4. To make it be a positive 1, it needs to be minus the 3. So I'll split the a terms power. So I still have the 3x, the GCF up front, but now when I split it, it becomes x minus 3 and x plus 4. I have factored the denominator. And we can now state by saying that we cannot divide by 0, that 3x cannot equal 0. So when you divide that by 3, we'll get that x cannot be 0. That's there. X cannot be 0. We would get that x cannot be positive 3, and x cannot be negative 4. All three of those values are undefined. But x could be any other real number. The domain could be any other real number. Now to figure out holes in vertical asymptotes, I will factor the numerator. So in the numerator, I'm going to take my factors of a, b, and c here. Let me put this in a different color here. A, b, and c. So we're looking for factors of 12 that add up to negative 7. So there's 1 and 12, 2 and 6, 3 and 4. Again, it's 3 and 4. The only way to get a negative 7, though, is both of these have to be negative. And if you check it, negative times a negative does give us a positive number. So I still have the GCF of 4, but now I have x minus 3 and x minus 4. All right, as I move in, I can see that I can remove this factor here. So since those cancel, that's a hole. X equals 3 is a hole. And so to find the exact location of that hole, you plug this into the simplified equation, which would be 4 times x minus 4 over 3x times 3x plus 4. So I'm going to plug in 3 to that equation to figure out where my hole will be located. So it's going to be 4 times, let's see, 3 times excuse me, 3 minus 4 is negative 1. I'm plugging in 3 is what I'm doing. And here it'd be 3 times 3. I'll do parentheses, 3 times 3. And then this 3 plus 4 is 7 times 7. So what does that equal to? That'll be 3 comma negative 4 over 3 times 3 is 9 times 3 is 63. Negative 4 over 63. The asymptotes would be the leftover factors, the domain breaks. So we have not used 0 and we have not used negative 4. Those are going to be vertical asymptotes. For the horizontal asymptotes, you look at your powers. It's either bigger on top, bigger on bottom, or the exponents are the same. Here I have a degree of 2, degree of 3, and bigger on the bottom. Since it's bigger on bottom, that's the rule of Bobo. Bigger on bottom, we get y equals 0. For the y-intercept, we're going to plug in 0 to our equation, so f of 0. If I plug it in up here, notice everything cancels except for the 48. If I plug it in the denominator, 0, 0, 0, those all cancel. So I'm left with 0 left over. And we cannot divide by 0, so this is undefined. F0 is undefined. There is no y-intercept. And this should make sense because we just wrote it up here in the domain, that we are not defined at 0. Any zeros can be found from the numerator if you set that equal to 0. 4 cannot equal 0, but x minus 4 could if x is 4. So we should have a 0 at x equals 4. So let's take a look at this one's graph. This might take a little bit longer to type in. We have 4x squared minus 28x, 4x squared minus 28x minus, or I think it's actually a plus 48. I think it's a plus 48. I'm going to check that. Yes. And then on the denominator, it was 3x cubed. 3x cubed plus 3x squared plus 3x squared, and it's 36 minus 36x minus 36x. So there's our equation. I graphed that. Can't quite see the 48, so let me bring that in just a tad. Put it up here. So there's our graph, and I'll take a picture of it and we'll load everything to the page. Oops. Okay, so the first thing we said, the domain, we should have 3 breaks. By vertical asymptote, I should have a break at 0 and negative 4. So here's 0. Here's negative 4. So I'll write that in here. That's x equals negative 4. This is x equals 0. We should also have a hole at 3. And then that's like really close to 0. At 3, 1, 2, 3. Really close to 0. That right there should be a hole. So let me add a hole in here. So there's our hole, and the location of that hole we got as 3 comma negative 4 divided by 63. That's the location of that hole. We had a horizontal asymptote at y equals 0. Try that again. Y equals 0 there. We have a horizontal asymptote. And we did not have any y-intercept, but we did have a 0 at 4. At 4, right here, 0, 1, 2, 3, 4. Yep, we have a 0, 4 comma 0. And so if we fill in our values, what happens as we go to the left? It looks like we're going to be approaching a horizontal asymptote at 0. What happens as this graph goes right? Again, we're approaching that horizontal asymptote at 0. We have a limit at negative 4. What happens on the left side of negative 4 is the graph falls to negative infinity. And then what happens on the right side of negative 4? On the right side of negative 4, we rise. These are not equal to each other, so the limit at negative 4 would not exist. The limit at negative 4 would not exist. Okay, and the next break we look at, so that was negative 4. Let's check out 0. 0 from the left, 0 from the right. As we go to 0 from the left, as we approach 0 from the left side, the graph rises. As we approach 0 from the right side, the graph falls. Again, this limit would not exist. Their values are different. And now here, as we approach 3, from the left, and then as we approach 3 from the right, both of them are approaching this point there. Both of the pieces are approaching that point, which we found to be negative 4 over 63. So these will be equal to one another, negative 4 over 63. Because that's the case, because they're equal, the limit as x approaches 3 would exist, and it would, whoops, I forgot the f of x. And it would be that value, negative 4 over 63. So, whole lot of practice there, a whole lot of practice on working through those. That's how we get through this algebraically. That's how we find all those values. Now, let's look at example 4 here. It says, well, this is a real-world application of a rational function. A rare species of insects was discovered on the Amazon rainforest. To protect the species from extinction, entomologists transferred a certain number of insects to a protected area. The population P of the new colony T days after the transfer is given by that equation there. First, find the y-intercept. So how do we find a y-intercept? Well, we plug in 0 to our value. So we would do P of 0. So P of 0 would equal, and when I plug in a 0 here and here, it's just going to be 50 divided by 2, which is 25. Now, interpret this in the context of the problem. What this means is at time 0, we have a population of 50 of this rare insect. So the insect's population at time 0, which is initial time. That's like our initial population. Our initial population. Whoops, forgot the N. Initial population is 25. Okay? So that's the initial population. It says find the limit as t goes to infinity. So as time goes on, what would happen? Now, one way you can do this, if you want to estimate, is you can put in a large number. So let's just say I put in like 1,000. That's a really large number. You can get an idea where this graph is heading to. So what I would have is 50 plus 25,000. That's why I did 1,000 just to make my number easier. Divided by 2 plus, now 0.1 times 0.01 times 1,000 is just going to be 10. So as you can see, what happens is this is going to become a really, really large number. 25,050 divided by 12, it's going to be something really large. Now, what does that mean? Without graphing it, that means the population is increasing over time. So the population is increasing. The population is increasing over time, which is good news. If we don't want it to go extinct, we want it to increase over time. So that's a good news, okay? Now that might be a real world context. Now we got to here, now it's your time to practice. Problems 1 through 9 here, all want you to work, I say 1 through 9, yeah, 1 through, let me make sure, 1 through 9, all deal with this same graph, and I want you just to answer questions about g of x here.